Newton's first law of motion, also known as the law of inertia, states that every object will remain at rest or in uniform motion in a straight line unless compelled to change its state by the action of an external force. A bike rolling down a hill will keep moving until it hits something, unless someone hits the brakes. Every object in the universe acts like that. Whether an object is stationary or is moving on a straight path, it will remain that way until something changes that fact. But the law assumes the lack of friction and other forces, such as air resistance. Newton's first law implies that a bike rolling down a hill will never stop moving unless something stops it. That doesn't happen on Earth, even if it doesn't hit anything or if someone doesn't hit the brakes. That's because the first law is only valid in a frictionless environment. There are microscopic irregularities in objects, and friction happens when the surfaces of two objects move against each other and cause resistance due to the irregularities. Simply stated, rougher surfaces have more irregularities and will cause more friction when rubbed against other surfaces. Meanwhile, smoother surfaces are less likely to produce lots of friction, but still have microscopic irregularities that can still produce friction. Newton's second law of motion. Newton's second law of motion in math terms is force equals the mass of an object multiplied by its acceleration, which is the rate at which the object picks up speed. That means that the force a moving object produces depends on how heavy and fast it is picking up speed. Similarly, the equation can be twisted to get the object's acceleration, which means that an object accelerates depending on how heavy it is and the force exerted on it. If you were in a grocery store with your mom and were asked to push the cart, when the cart is still empty, it doesn't take too much effort to push it forward and allow it to pick up speed. But as your mom puts more stuff in, the effort required for it to accelerate is now more significant. This explains why balls are more accessible to push than boulders. At the same time, a moving object that's heavy and picking up speed rapidly can also produce more force, which is why a runaway truck is more dangerous than a runaway sedan. But the same law also means that lighter objects can move faster than heavier objects when the same force is applied. So if you place a V6 engine inside a sedan, it will move faster than a pickup truck with the same engine as long as all of the other variables are unchanged. Newton's third law of motion. This one can best be summed up with the saying, for every action, there's an equal and opposite reaction. It sounds like karma, basically what goes around comes around, but that isn't entirely the case. According to Newton, when you move, there will always be an opposite reaction exerted by another object. The mere act of stepping on the floor already produces that reaction. A step produces a force that is exerted on the floor. Meanwhile, the floor exerts the same force back to our foot in the form of resistance, allowing you to feel that bounce in your step. If the floor doesn't produce the same reaction, you won't be able to move forward because your foot will only end up sinking. It's similar to the recoil from firing a gun. When you pull the trigger, force is created to propel the bullet forward, but the same force exerted on the bullet to propel it forward also pushes back, which causes the gun to recoil. The bizarre part is that this law applies to objects that aren't in motion. Gravity's force of attraction pulls your desk down to the floor, causing the floor to exert the same force on your table, allowing it to stay where it is. The law of universal gravitation. I promise, this is the last Newton's law. According to Newton, any particle of matter in the universe attracts any other with a force varying directly as the product of the masses and inversely as the square of the distance between them. It sounds like a mouthful, but it simply states that an object with a greater mass produces a stronger gravitational force. The law was used to observe our solar system and explain why all the planets circle the sun. The sun is the most massive object in our solar system, producing a stronger gravitational force than any other celestial body close to it. It's not as if the other planets don't produce their gravity, it's just that the sun is so massive that its gravity makes it the centerpiece of our solar system, accounting for 99% of the solar system's mass. Newton's law says that the distance between two objects also dictates the force of gravity they produce. This explains why the inner planets in our solar system are smaller than the outer planets. They have relatively low gravity and cannot attract large amounts of gas to their atmospheres. In contrast, planets like Jupiter are so giant that they produce enough gravity to pull more materials and gas toward them. Conservation of energy. The principle of conservation of energy states that energy can neither be created nor destroyed, but is only transformed from one to another. In this case, energy is a basketball that passes from one player to another. It will still always be just one ball. Its appearance might change due to dirt or wear and tear, but it's the same ball. This means that the energy in our world already exists and is never created out of thin air. We just convert energy. In the biological world, plants convert solar energy into food to survive. Animals convert the plants into food, which other animals or humans eat for energy. In this case, energy was never created, but transformed and transferred from one object to another. It can't be destroyed either, so when an animal dies, its remains go back to the earth to be used by plants for sustenance. As they say, it's the circle of life and how the conservation of energy works. That was bad. So no energy is created when we create or generate energy with our power plants. They simply use energy from different sources and transform it into usable energy, electricity. For example, solar panels don't create energy from the sun, but only transform solar energy into usable energy. In this case, energy conservation is a game of give and take, where the universe keeps passing around energy that has existed for as long as the cosmos has existed. The laws of thermodynamics. First, the 0th law says, if two things are in thermal equilibrium with a third thing, they're in equilibrium with each other. It's the ultimate mediator between two different systems with different thermal readings. It keeps the peace between two temperatures in a proverbial boxing ring. Then there's the first law of thermodynamics, based on energy conservation law. You can't create or destroy energy. This forms the foundation for understanding heat transfer and how energy is converted in different thermodynamic systems. After all, thermodynamics is the study of how heat and energy work and move within a system. The second law of thermodynamics states that some energy becomes unavailable for work when energy is transferred or transformed. This is the concept of entropy, the amount of disorder or randomness within a system. Simply stated, energy gets wasted in any process, but isn't destroyed or rendered unusable in a system. When that happens, things become more chaotic. Combined, the first and second laws of thermodynamics explain why perpetual motion machines, or machines that can move without an external energy source, are impossible. It violates the fact that energy can neither be created nor destroyed. Moreover, according to the second law, a machine will eventually lose energy to friction or heat and stop moving. Finally, the third law of thermodynamics says reaching absolute zero temperature is impossible. This is because the third law states that the entropy of a system also approaches zero as the system's temperature reaches absolute zero. As you get closer to zero, the randomness explained in the second law also decreases and goes down to zero. This violates the laws of physics because the second law states that a system will always have entropy. Maxwell's equations. Maxwell's equations are fundamental equations that describe how electric and magnetic fields behave and interact. Think of these equations as the ultimate cheat sheet that explains how electricity and magnets work. The first is Gauss's law for electricity, which describes how electric charges create invisible forces called electric fields that can push or pull other charges. Meanwhile, Gauss's law for magnetism talks about how moving electric charges or changing electric fields can produce magnetic fields, invisible areas around a magnet that can influence other objects or move charges that also have their fields. The third is Faraday's law of induction, which says that moving a magnet near a wire can make electricity flow in the wire. We make electricity in a wire simply by moving a magnet or changing a magnetic field. This is precisely how generators work. Ampere's law, with Maxwell's addition, states that an electric current in one wire can create a magnetic field that loops around it. But Maxwell added that magnetic fields can also be produced by changing electric fields, allowing us to see a bigger picture of how electric and magnetic fields interact. Ultimately, these concepts allow us to understand how electricity and magnetism work with one another and how they are interrelated in many different fields and technologies, such as communication devices, power grids, and even MRI machines. The principle of relativity. When you're in a moving bus and doing all sorts of activities with your friends, such as throwing a ball around, everything seems normal to you and everyone else on the bus. But things are a blur for someone watching you from the sidewalk, because they only see a bus moving at 80 miles per hour. They may see the ball moving, but it's moving at almost the same speed as the bus. That's the principle of relativity in action. Simply stated, the principle of relativity states that the law of physics are the same for everyone, no matter how they move. Whether you're conducting conducting an experiment inside a train or in an office building, the results will always be the same because of this principle. It's the referee who keeps everything fair in a heavyweight physics bout. The twin paradox applies this principle. Here, one twin stays on Earth, while the other travels near the speed of light. The one on Earth ages at the same rate, while the one traveling in space ages slowly because time moves slower for objects moving fast. So by the time the space-traveling twin returns to Earth, he will be older than the one who stayed home. So whether you're standing still or moving at the speed of light, the principle of relativity says that you still have to follow the same rules of physics that everyone else does. No special treatment in physics exists, regardless of how fast you're going. The standard model of particle physics. The standard model of particle physics is a theory that describes how elementary particles interact through three fundamental forces: electromagnetism, the weak force, and the strong force. It's like a puzzle that tries to explain how atoms or particles work together. Or think of it as a giant Lego set, with every brick representing particles. The instruction manual that comes with the Lego set represents the standard model of particle physics. Particles are divided into two categories. The quarks are the protons and neutrons, which are at the center of the atom and make up the nucleus. Meanwhile, the leptons are the electrons, which surround the nucleus, or core of the atom. These particles interact with one another in different ways, but you can think of them as different types of forces. Electromagnetism, for example, is the attraction between magnets. Meanwhile, the strong force holds quarks together inside protons and neutrons, similar to how you might want to use glue to hold Lego bricks together. On the other hand, the weak force helps particles change types, like how you might want to swap different Lego bricks with different colors.